So.
Thank you. So this is this lecture will be probably the least technical, and actually it may be even be short. Let's see. So one thing I wanted to do first, in this lecture I will talk about a couple of barriers. I mean, we already have talked quite a bit about the stable fixed point barrier for algorithms. And in this lecture, we'll talk about the low degree likelihood barrier and list some connections and open questions. But before I get to low degree algorithms, I just wanted to sort of formalize this stable fixed point barrier that we spoke about yesterday a little bit more in terms which are more complexity oriented. Meaning I want to talk about it in terms of detection instead of recovery. So what is the stable fixed point barrier? So it's quite a general hardness assumption. So instead of trying to define it, in its generality, I'll try to define it while I give an example. Okay, so you can say that it says that two distributions on D null and D1 and D2. Let's just call it D1 and D2 on constrained graphs, on constrained hypergraphs. Constrained hypergraphs are indistinguishable. Okay, so what are the two distributions and how is this defined? So the way I like to think about it is in terms of these little Lego blocks for vertices and edges, vertices and hyperedges that you can put together. So let me just show what I mean. So imagine you had the following two kinds of blocks. Okay, your vertex, which looks like this, and it has D edges coming out of it, and on each edge there's an incoming message and an outgoing message. They are half. Let's say the numbers. There are two messages on each edge. Let's just say they're half and half for now. Okay, this is one kind of a Lego block you have. The other kind of Lego block you have is you have a half and half coming in and half going out. Basically, you have these little you have these you have these Lego blocks for vertices and hyperedges or edges. They have terminals on them, and on these terminals you have incoming and outgoing messages. Okay, and these incoming and outgoing messages are some numbers or some distributions over 1 through k. Okay, and the block itself is calculating the messages correctly as per the rules of BP, meaning the outgoing message on U to V is correctly equal to the correct function, some function of the incoming messages from all the other nodes. Okay, so you have you have blocks like this, right? There are two ways to sample. Okay, so firstly, whenever you have blocks like this, it gives you a distribution of local distribution or states of the system. For example, if I look at this vertex, this vertex can be in the all zero state or all one state. Or basically the vertex can be 0 or 1, right? The vertex can be 0 or 1. Okay, and depending on the messages, you can calculate the probability that it is 0 and probability that it's 1. Okay, and similarly, if I look at an edge like this, it can be in state 0, 0, 0, 1, 1, 0, 1, 1, right? The two different 4 states. And you can calculate the local probabilities of these 4 things. Okay, so all of this I can do just if you give me the Lego blocks. For each block, I can write down the probability for all the local configurations just by the BP rules. And I have these Lego blocks. Now, there are 2 ways to build a graph or a hypergraph out of this. Okay, one way is you take the, okay, let me actually draw another piece. Like, let me draw another piece here, which is, actually I should use a different color. Green, yeah, okay, green is good. So you take green. So green is integral, meaning the state of this vertex is 0, and it sends 0 on all the edges. Okay, and so the state of this edge is, I don't know, 0, 1, right? That's what. So this edge is going 0, this edge is 1. Okay, so that's the integral thing. So you have the fractional Lego blocks and the integral Lego blocks. Okay, you can take the fractional Lego blocks and make up a graph. Your only constraint is, you know what is a graph? Well, how do you connect a graph? Well, you take all your, so D1 looks like this. So you take a bunch of vertices. And a bunch of edges. Okay, and this is how you sample a deregular graph. How do you sample a deregular graph? You sort of construct a matching, right? So here you need to just construct a matching so that, let's say the messages on this vertex are 2/3 and 1/3. Let's say there is a 2/3 and 1/3 here. Okay, you have to connect it to another node for which the outgoing is 1/3 and 2/3. Okay, so if this vertex V says it's on this edge, I send out 2/3, I get a 1/3, and this hyper edge says on this edge I receive a 2/3, I send out a 1/3. Okay, these two can be matched, right? And similarly, so it's a configuration model for generating a random graph where you have these Lego blocks and you connect up edges where the incoming and outgoing messages agree. Okay, that's a model of graphs. You get a random graph that way. Okay, another configuration model is the green configuration model, where you match up the actual values now. So instead of so you have the green things here, 0, 0, 0, 0, 0, 0. Oh, sorry. You just have the actual values here, 0, right, and 0, 1, right. So this hyper edge wants to connect to a vertex which is labeled 0 and on one side and labeled 1 on the other side, and this vertex wants to just connect to an edge which is labeled 0 on one side. So they connect. So that in the two graphs are generated this almost the same way. The only difference is one of them is actually matching the fractional messages on these dangling endpoints, and the other one is actually matching the integral values. Okay, and the two are indistinguishable if the fixed point. Well, this is going to always give you a fixed point, just because you'll get a fixed point here purely because you're actually just matching messages when you connect edges. So you'll always be at a fixed point, no matter what value you write down here. This is so. If your infinite tree that you have with these messages is stable, then these two distributions are indistinguishable. these two distributions or hypergraphs are indistinguishable. That's what the stable fixed point barrier is. And I guess to sort of say why this is, why I had to state it this way, I like to think of it this way because this way generating a fixed point is easy. The fact that you start a fixed point is easy as long as you match the messages that are leaving. So on this edge, I said it's 2/3, 1/3. As long as I connect it to a 1/3, 2/3 edge on the other side, it's going to be a fixed point. So, but basically, stable fixed point barrier says that these two distributions are indistinguishable, and so it's really a decision problem hardness, and a very general decision problem hardness where you can't decide between two graphs, and its implications for recovery itself is still it's quite subtle. Meaning, let's take stochastic block model with some parameters, and you're trying to recover the communities. Well, maybe the naive fixed point is not stable, so you get out of the naive fixed point. Maybe there's a different fixed point which is stable, and the question then is that different fixed point, which is not the optimal answer, but some other different fixed point, if it is stable, that could be a bottleneck for recovery going beyond that point in some sense, because maybe if your algorithm does get stuck there, it has this stable fixed point barrier says you can't get out of that barrier. So so it's unclear how to use this to talk about recovery itself, because it's really a hardness of distinguishing, and it's really saying that if you are given a graph at some particular fixed point, you don't know how to get out of it. And it's subtle what will happen to problems where there are multiple fixed points. Maybe the naive one is not stable, but there may be other ones which are stable. And are they really bottlenecks for recovery or not? We don't know. Maybe your algorithm never reaches that point, so it never needs to get out of it. It's very unclear what the situation is. So anyway, so recovery seems to be very, very unclear what the situation is. Okay. Okay, so now we'll talk about another barrier, which is comes about by thinking about low degree polynomials as algorithms. So a general low degree polynomial, we're going to think of as an algorithm. In particular, let's say our proxy for a polytime algorithm would be an order log n degree polynomial of the input. Well, not all log n degree polynomials can be computed in polynomial time, but at least they can be computed in quasi-polynomial time. So let's just, and we want to keep it looking at log n degree polynomials precisely because we want to capture many of the standard algorithms. In particular, if you look at log n degree polynomials of the input as a class of algorithms, it captures the following things. It captures the power method. Because typically what does power method do? You have a matrix A and you raise it to the power log n, right? Or a to the power t, where t is log n. And you look at the trace of a to the t, let's say. And this gives you a good estimate of the largest eigenvalue of the graph, of the matrix. So the power method, which is at the heart of spectral algorithms, is a log n degree polynomial. And of course, here I say it's a log n degree polynomial under the assumption that t is order log n. There may be situations where you actually need to raise the matrix to a very high power, and it might be important to do that. Okay, and then of course, order one iterations of BP or AMP clearly fall under this class. And then, of course, local algorithms. On sparse graph. And by the way, I should say for anyone who is going to watch this offline later on, please stop watching this video at this point. Or you're much better off watching the many different talks of Alex Wine, which are there online, of which this is just a derivative. So they're way much better, and they're online. So you should check them out. It's very nice and comprehensive. So so those are our algorithms. So then we can talk about low degree indistinguishability. So we again talk about detection problem. So detection problem, you have or distinguishing problem. You have a sample from Pn or Qn, two different distributions, planted or null. You want to distinguish between the two. And what would a low degree algorithm do? Well, as a candidate low degree algorithm would do the following. So you would have a polynomial f that takes the input and outputs a real number. Okay, and let's say it's a low degree polynomial. And what you'd hope is that under the planted distribution, the value of the polynomial is large. You'd want that f of y, if y is from the planted distribution, this is large, and f of y, if y is from the null distribution, is typically small. And then you have a way to distinguish between the two distributions. Okay, and so that that's the goal. That's a reasonable thing to try. And the really, nice thing about low degree polynomials is that they're such a nice, almost simple, silly class of algorithms that you can actually take away the creativity and write down what is the best algorithm in that class easily. In particular, the best algorithm, in a sense, would be given by the output of an optimization problem. So what is the optimization problem? Well, so I have some function f, a low degree polynomial f that I want to find. And what do I want it to be? I want it to be the case that in the planted distribution, the function is large, so its expected value is large. And in the null distribution, the value is small, so the expected value is small. So in fact, I'm sort of interested in the ratio. It should be much larger in the planted distribution as opposed to the null distribution. Okay. So in particular, what I'd want to do is I want to maximize like the mean value in the planted divided by the typical absolute magnitude in the null. Typical magnitude in null. Okay, and so this is the nice quantity, and if you find the best such polynomial, it tells you the best algorithm in this class. And like the advantage of D is how good the best algorithm does here. Okay, so in particular, if this advantage D is order 1, then you know that low degree polynomials succeed. I'm sorry, I want to say fail, but let me change this. It's omega 1. If you find a function f such that its value in the planted is much higher typically, then you say low degree polynomial succeed and distinguish between the two cases. And then if it's literally order 1, if it's sort of for same order of magnitude, then you have low degree polynomials fail, right? So this class of algorithms, low degree polynomials, such a nice continuous compact set of algorithms that can actually search or that can define this quantity of them. And and in fact, the way this quantity is defined, it's actually possible to go one step further and make the entire optimization problem almost trivial. So here's what's going on. So this is what we want to maximize. We want to maximize this ratio of these two expectations. Okay, so let me write this a little bit more carefully. So what do we want to do? We want to find a max over functions with a degree of f at most d of the numerator I'm going to write the numerator in also as an expectation over the distribution Q. Okay, so I'm going to write the numerator as expectation dq by dp. This is the likelihood ratio times f of y. Well, this is just the likelihood ratio, or the density. You could say this is the density of Q with respect to the measure P. Sorry, did I make a mistake here? I think I should say dP by dQ. Yeah. So y from Q. That's the numerator. And the denominator is square root of expectation from y from Q of f of y whole squared. Okay, so if I see, so now you have the same sort of expectation, the numerator and denominator. Really, how the way it looks like is you have a inner product between a function L and F, where L, suppose I define L of y to be the likelihood ratio dP by dQ of y. Okay, this is the inner product under the measure Q of L inner product F divided by the 2 norm of F also under the measure Q. Okay. So, you know, we set up the definition of this ratio in a nice way that we are just doing Euclidean geometry in this this space. So everything is Euclidean. You have a 2-dimension. You have a 2 norm here. You have a 2 norm under that space, and then you have a usual inner product there. So therefore, the function f that maximizes this is really just the function that completely aligns. Right? It's just a projection of f onto the space spanned by, or projection of L onto the space spanned by f. Sorry. So let me see. So it's a degree of f is d. So you're looking for the best degree d polynomial that has a highest alignment with a given function L. Okay, and the best polynomial that has a highest alignment with this given function L is just the low degree part, low degree projection of that function. So this is actually equal to the 2 norm of L, the L less than d, which is you take L as a function, as a function, and you project it onto the span of low degree polynomials. So it's projection of L onto span of degree d polynomials.
Are you assuming something about Q here?
Nothing as yet. So far, it's just I haven't assumed anything about Q. Basically, in any under any measure, you still have a span of low degree polynomials, and you're just projecting onto that span. Okay. And now, you know, in fact, if your Q is nice, like if Q is IID Gaussian, or if a Q is an IID distribution, then it's quite easy to write down the projection of a vector, a projection of any function L, just because it's just given by the Hermite coefficients or the low degree Fourier coefficients of that. So for example, if Q is uniform on plus minus 1 to the n, right? So what is the 2 norm of L less than d whole squared? This is the quantity that we're looking at. Well, it's just sum over all subsets smaller than d of the Fourier coefficients of the likelihood function. So this is, I mean, it's usually, it's often quite easy to calculate these quantities. So that's the kind of the advantage of this whole approach right now, is that we can actually start calculating these numbers for many choices of P and Q, distributions P and Q. Okay, and what actually comes as a surprise is that even this simple class of algorithms, which is low degree functions, actually seem to capture the complexity of many of the problems. So in fact, for many detection problems, it seems to be the case that when low degree polynomials fail, all known efficient algorithms fail. And this has happened quite in many cases, like the planted clique, the two community stochastic block model, or the tensor PCA, and many of these things. And what's kind of very nice to see in all of these cases is that you can just use this low degree polynomials class as a way to figure out what is the threshold at which this problem should become hard, and it matches our existing ideas about when this problem should be hard. So it's quite nice. In fact, based on these observations, Hopkins made this conjecture in his thesis. I'll just write down the conjecture. It's quite a powerful conjecture. So you suppose you have a distribution Q, you have a null distribution Q with IID entries. Okay, it's like a product distribution. Okay, your planted distribution is symmetric. So by symmetric, the way it's stated, your planted distribution is probably if it's a distribution over graphs, then it should be symmetric over permutations of vertices. If it's a distribution over 3 uniform hypergraphs, then it's again symmetric over the permutation of vertices and so on. So that's the symmetry you need. And then let's assume that something more than log n, like log n to the 1 plus epsilon degree polynomials fail to distinguish P and Q. So then the conjecture is that for any delta bigger than 0, no polytime algorithm distinguishes P and Q, distinguishes P and a noisy version of Q. Sorry, Q is already noisy, right? So Q and noisy version of P. Okay, this is the conjecture that Hopkins states in his thesis. And it's a hardness assumption. It's quite a bit stronger than many other hardness assumptions. In fact, the most surprising thing about this, like at first glance, is that it's 2021 and I'm still stating this conjecture. It's not disproven. And that's probably the more fantastic thing about it, that such a strong conjecture is actually still true, and it makes the right predictions. So that's the really nice thing about it. And so recently, Holmgren and Alex Wayne, they sort of stress tested this conjecture a little bit. So they showed that symmetry is necessary, and essentially, because if you don't have symmetry, you can have things like error correcting codes with large dual distance. So locally, the variables look independent, like the span, like a k-wise independent distribution. Locally, they look independent, but globally, they're distinguishable. Now, alternately, if you have real valued entries in Q, then you have to be careful with the noise model that the way you add noise to the planted distribution. So what you should do is you should make sure that you have some additive noise. If you don't have additive noise, then you can start encoding bits into the real numbers, and then you can make them distinguishable. So, but this is a conjecture that that no polytime algorithm distinguishes these two, and it seems to be true in all of the cases that we have seen so far. And in fact, probably the most surprising and strongest evidence of it is in the case of stochastic block models. For stochastic block models, Hopkins and Steurer, they showed that the prediction of this low degree conjecture exactly match the Kestenstiegem threshold. So in particular, it exactly matches this stable fixed point barrier that we spoke about. So that's nice. And so in fact, that's very surprising. And in fact, I guess one open question, which I think it's been nice to have, I don't know if it's really, maybe it's not that hard, but I think it'll be nice for if somebody does it, is to actually prove that the predictions match for Bayesian CSPs. In particular, do it for the general class of Bayesian CSPs is just a technical annoyance. Let's say even fix some nice CSP, like not all equal SAT or something like that, and not all equal 3 SAT or some other nice enough CSP, and show that in that case, the point at which low degree polynomials fail is exactly matches the predictions of BP fixed point stability. Yeah, that'll be a nice sort of a thing to confirm.
Do we know connection between this and SOS?
Between low degree indistinguishability and SOS. Yeah, so yeah, right. I should add that. So so low degree indistinguishability did come out of pseudo calibration. The idea stemmed out of pseudo calibration, which was a technique to prove lower bounds for SOS. And I guess one of the, I guess probably the main open question in SOS lower bounds is to prove that low degree indistinguishability implies a SOS hard. This is, I guess, goes without saying, this is like the main open question. SOS hard, as in it's hard for SOS SDPs to distinguish. This I think this is the main open question of SOS lower bounds. In particular, it should technically imply many of the SOS lower bound questions that I asked earlier in these lectures. It should imply them. So yeah, but we're I mean, there's a whole lot of literature on this. Maybe I'll talk about it a little bit later if we have time, if you have interest. Okay, so the next thing I want to talk about is, so we've been looking at low degree polynomials as an algorithm for distinguishing, but you could also think of them as an algorithm for recovery. So what is the recovery problem? Well, you have some joint distribution X and Y, and what you want to do is, inference, given Y, you want to estimate X. Okay, you want to estimate X recover. And let's just decide that we are going to compute a low degree polynomial and output the value. Okay, just for, let's just decide that. And once you decide that, there's some sense the best thing you can do. The best thing you can do is something that maximizes the correlation with your original X. And that's an optimization problem. So you can write down that optimization problem as I've written here. So what are we doing here? We are trying to find a low degree polynomial that maximizes the correlation with the original X. while normalizing, of course, the length of the vector that we output, right? So given the length of the vector, we want to maximize the correlation, the original X. So in some sense, this is the most obvious natural thing to try here. Okay, and you could ask, right? Like I guess a question that you could ask is, okay, so this is a very natural limit to how well you can recover, right? The best low degree polynomial recovery is a natural limit on how well you can recover, and it's natural to wonder how it relates to all of the other natural limits to how well you can recover that you get out of BP. In particular, here's a question which it will be nice to investigate. Is okay, let's call this the optimal low degree recovery. Okay, you have an optimal low degree recovery function. Okay. How does it relate to all of the theory around BP fixed points and everything? Because remember, yesterday we said for example, optimal base recovery rate is sort of characterized by things like fixed points of BP. Okay, so you expect that if you try to find the best low degree polynomial that's the best polynomial for, let's say, 2 community SBM. Somehow, when you try to do that, solve that optimization problem, the Fourier coefficients of the function and the function itself should scream out BP, right? Somewhere it should be there. If we believe that both of these give you the same optimal answer. And so this will be a nice question to investigate. Like, what is the connection between BP fixed points and sort of the low degree recovery function, the optimal low degree recovery function, which is the optimum of this program that I wrote down here. And I guess the key, okay, so this, the key difficulty with this program that we wrote here is that unlike the earlier program, over here, we don't have, sorry, I should use P here. We only have the planted distribution in both the numerator and denominator. So in particular, in the earlier calculations that we did for detection, we had the null distribution Q, and we moved all the calculation to the null distribution. And the null distribution was nice because we sort of dealt with cases where the null distribution is a uniform distribution. And out of the uniform distribution, low degree polynomials, it's easy to find an orthonormal basis for low degree polynomials. That's Fourier analysis or Hermite analysis or all the things that we have. But if you're doing the entire optimization over planted distribution, for example, if this is the distribution over graphs produced by the stochastic block model, okay, if it is really that, then there's no nice basis for low degree polynomials under that distribution, because edges are no longer independent. There's a lot of dependencies between the edges, and therefore, although I can write this optimization problem, the reasoning about the value of this optimization problem or finding the best possible F for here, calculating it seems much harder than earlier because of that reason. So, and that's the reason why even this question that I stated at the end is quite non-trivial, because you have to somehow get a handle on the optimal low degree recovery function, which is basically you have to get a handle on the projection of the optimal recovery function onto low degree polynomials. Okay, but even given that, there are works, quite interesting works, which deal with this issue. In particular, there's a work by Sleel and Alex, where they where they deal with this issue of not having a nice orthonormal basis for low degree polynomials head on, and they prove that for these two problems, planted submatrix and planted dense subgraph, for these problems, there's a detection recovery gap, where it's meaning there's a region where detection is easy, but recovery is still hard for low degree polynomials, that is. Okay, and in a quite a bit of an orthogonal direction, there are a sequence of works which use the overlap gap property to directly bound the best load, the performance of a best low degree polynomial. The idea being low degree polynomials must be stable, and if you have overlap gap property, stable algorithms are not good. So this was I think Boaz outlined this argument, and this argument is very nice. It's been used right now for p-spin glass models and for independent sets in random graphs. Right now we have the best lower bound against low degree polynomials, which is 1 plus epsilon log d over d. And more recently, like Guy and Bryce, they have a lower bound for KSAT. For KSAT, they show that there's a region of the density which matches the best known algorithm so far, beyond which no low degree polynomial can recover the assignment. And all these works use overlap gap property as a way to attack this issue of how do you identify the best low degree recovery function. Instead of identifying the best low degree recovery function, you just directly prove that no low degree recovery function works because of overlap gap property.
Prasad,
yes.
Can I intervene a little bit? Hi, this is Elias. I want to say that I think that in the overlap gap property that you're mentioning, it has been properly applied for non-planted models. So like these words that you're mentioning are for non-planted models. So these are not about estimation, right? So the overlap gap property for estimation is quite a different beast. I mean, that's
right. Yeah. So So I guess right. So yeah. So right. The way we started out, we were talking about you're saying right. Yes. Right. Yeah. This is right. Yes. So KSAT is. You're right. So KSAT, for example, KSAT or large random graph, these are all non-planted. Yeah, that's right. Yeah, that's right. Yeah, right. Yeah, thanks. That's an important distinction. These are all. There's no planted solution in these problems or in these lower bounds, but the lower bound is still showing that low degree polynomials cannot solve the recovery or cannot recover the recover any good solution.
Yeah. I mean, it's more about like these are more about optimizing, right, the noise.
Right.
So, yeah.
They cannot recover any solution with good values. Yeah. Thanks. Okay. So finally, I wanted to mention this more recent result on statistical query algorithm. So just to refresh everyone, so a statistical query algorithm is a model of algorithms where your algorithm doesn't get access to the samples from your distribution, but only gets access to expectation of functions from your samples of distribution. So your statistical query algorithm is allowed to send function phi to an oracle. The oracle, I think of it as samples, takes m samples from the distribution D, and it returns the expectation, the empirical average of the phi values on the samples. So in particular, what you get back is the expectation of phi plus some sampling error. And the sampling error is just what you expect it to be. If you had m samples from a distribution, you'd have this error. So that would be a statistical query algorithm where somehow it doesn't have access to the samples, but only expectation of functions under the distribution, empirical averages on m samples. And you measure runtime based on how many queries such a algorithm must make given the accuracy M. So the accuracy parameter here is basically M, because that determines how good an approximation to the true expectation you get back from the oracle. And for a given accuracy parameter M, you can ask how many queries does your algorithm need. Okay, so the number of queries made by SQA is its runtime. Okay, is a proxy for runtime. Okay, and recently Brennan, Bressler, Hopkins, Lee, and Schramm, they show that for the problems like distinguishing planted from null, statistical query algorithms are more or less equivalent to low degree tests. And beyond the most obvious, the most natural and canonical bottlenecks between statistical query and low degree tests, they're basically equivalent. And so that's quite nice because they get statistical query lower bounds that way, and they get low degree tests. Yeah. And so I guess that's all I wanted to say about barriers and open questions. Yeah, I guess I'm finishing early. If there are any questions, I can answer.
What's the tolerance required for this?
Sorry?
What's the tolerance at which this equivalence holds?
Oh, what's the tolerance? So I think what they need is like, so I think what they need is like yeah, I should maybe not say anything if I'm not very sure. I think they need that so.
I mean, like, if I have an SQ algorithm which works at tolerance 1 over log n, what does that imply?
So the SQ algorithm tolerance being like 1 over square root m corresponds roughly to the concentration you get for m samples, like with dimensions inequality. And then that's like the m sample test. Like we get a correspondence between that SQ algorithm and the low degree test, which has access to m samples. So it's like it's supposed to, like in the statistical query algorithm, the tolerance is supposed to be a proxy for the number of samples that you get, which is a proxy for the signal to noise ratio. So like basically up to polylogarithmic factors, we show equivalence.
Up to polylogarithmic.
Up to polylogarithmic.
I was asking because for Ising model, for instance, you can do it with log n sample. So what would the implication be there?
There's a SQ algorithm with log n samples.
So there is an algorithm with log n sample, and it's probably SQ.
I guess it's like we should discuss it because there's a lot of parameters. So
One has to check.
Any other questions?
Maybe can I add a quick small remark about the OGP for maybe this is related to what Elias was asking or pointing out. So maybe one general direction that seems to be challenging is ruling out low degree polynomials for planted problems using OGP. But there has been some really interesting work on OGP and planted problems. So I guess the main one I'm aware of is Elias and David Gamarnik have a nice paper on planning clique. So exciting direction, I think, to think about that. Oh, and there seems to be maybe one more question in the chat. I'm not sure though what it is.
Yeah, so it's right. Do you have any? Okay, so the question was, how are there ideas on extending stable BP fixed points beyond constant degree? Yeah, so that so the question comes down to, if you look at 3XR, we've been talking about stable fixed point barrier and so on, and you can calculate the barrier for stable fixed point barrier for 3XR. What you end up proving is that what the barrier tells us is that for any constant degree 3XR SAT, finding any doing recovery beyond trivial is computationally intractable. So basically, all of the theory that we spoke yesterday, it sort of throws up its hand and says, oh, for no constant degree, it's easy. So the picture will just be, it'll be hard for all degree, which is true. And I guess, but the interesting thing is the 3XOR does become easy once the degree is more than n to the 3/2. And I haven't, yeah, it's a nice question to see if there's a general theory. What's a general theory to make predictions on those things? Yeah, I think there is work on Kikuchi hierarchy, which sort of explains the n to the 3/2 exponent, I think. But yeah, I don't know if there's like a very broad general statistical physics predictions. Maybe it's for the statistical physicists to tell us this is the prediction of when these problems should be easy or hard, such things.
Yeah, Prasad, given the strong conjectural and sometimes not beyond conjectural connection between SOS and low degree polynomials, is there a way to reformulate certificate problems, refutation problems in terms of low degree polynomials by some kind of, I don't know, relaxation of the SOS and so on? Is, for example, in going back to your earlier question about alpha 2 and alpha L for the largest independent set, can I rethink of this question in terms of low degree polynomials?
Yeah, we actually we don't have a way to do it yet. I mean, even the current technology for proving SOS lower bounds, like one of the promising approaches is to construct a planted distribution and sort of look at the problem of distinguishing the planted from this null distribution. Construct a planted distribution where the clique size is 1 over root d, and use the planted distribution to show the lower bound. So in some sense, it's not intrinsic. It's whenever if you construct a planted distribution and we are reformulating refutation as distinguishing problem, and maybe for some planted distribution you can prove the lower bound. For some planted you cannot prove the lower bound. In particular, it's not clear. There's no canonical way to construct change refutation to become like distinguishing, where we have all the low degree likelihood ratio and everything set up. Right. So basically, there is no canonical reduction from refutation to distinguishing, and the low degree technology is always well defined for distinguishing. All the low degree likelihood principle and all the low degree likelihood ratio and everything is good for distinguishing. For refutation itself, directly, there's no canonical approach. But one would hope that in any problem, for example, independent set in random deregular graph, in principle, one would hope that, okay, maybe the most naive planted distribution you can construct actually gives you the answer, but it can be tricky. Like, I think, for example, I think for max cut, we don't have a planted distribution, a candidate planted distribution, which matches the refutation lower bound, what the refutation lower bound should be.
Any other questions? Does anyone else want the mic?
Can I ask something also from the Zoom?
Of course, yeah.
So I have a question about this equivalence here, like between SQLs and low degree tests. Like, I have been thinking for some time that low degree tests are like naturally robust. I mean, you maybe kind of implied it also before, but I was never aware of a result about SQ algorithms being robust. That might be me missing some literature. Like, is there some fundamental reason we expect SQ algorithms to be robust? Because under this equivalence, they seem to be, right? Or somehow,
right.
I don't know. Like, basically, I'm just asking out of not knowing. Yeah.
I don't know what, like, SQL algorithms are naturally robust in one sense, right? Because if you're really taking M samples and giving away the averages, if a few samples are bad, you still.
I see. So there is this averaging. You're right. I see. But somehow this equivalence matches the robustness level. Is there such notion also, like between the two?
Actually, I mean, even I don't understand this very well. Maybe someone in the audience can tell me. I mean, there's another notion of robustness, which is more, is that you perturb the entries of your X, right? And low degree polynomials seem to be robust for that, like perturbing small number of entries, like random noise on the entries. Is there an intuition why statistical query algorithms are robust to that? Yeah, I don't know.
Statistical query, one of the original motivations for inventing it, as far as I remember reading this paper, was that it's robust to certain noise models. I think that was one of Kern's motivations. Actually, wasn't to prove lower bounds, but actually an algorithmic framework for thinking about constructing robust algorithms that are robust to noise.
I see. So given this, like, we're discussing in this workshop about the power of efficient algorithms, but it seems to be efficient, robust algorithms, or is this like a kind of?
I should predicate that all the things that we talked about is in a sense efficient, robust algorithms, in the sense that once you allow for general algorithms, there's always the Gaussian elimination, which is there, which break all the theories that we speak about algorithms. Yeah.
And maybe if I can use a few more seconds of your time, like on this, on the last equivalence, like I want to ask actually maybe the people also in the audience that were part in proving this, like there is also like some sub-exponential time, right? That the low degree method yields as maybe the optimal sub-exponential time in the hard regime will be, like they say that you cannot solve this polynomial time, but maybe, you can solve this in that sub-exponential time. Like, is there, I guess the SQ model also gives some prediction about sub-exponential time. Like, were they able to prove this equivalence also in the hardware with respect to accurate quantified statements that are that precise sub-exponential time-wise, if this makes sense?
I don't know, maybe.
Yeah, I can answer this. I actually wanted to say one more thing about the previous. Sorry for spending so much time on this SQ thing, but okay. So one more comment about the noise robustness. So actually, we have some requirements about the distribution, which also is necessary in order to make the problems equivalent, because the issue is that statistical queries are not bounded in runtime. So that makes them not a good, like the proxy of number of queries for runtime isn't very good. For example, in planted clique, like you can always have a statistical query that just asks, is there a clique of size at least k in the graph? And so somehow SQ, like it's not very good for one sample problems. It's really good for problems where the number of samples measures your signal to noise ratio. So we have to do something to kind of tie the hands of the statistical queries algorithms behind their back and level the playing field, right? So somehow this also makes it difficult to talk about like robustness, because in some sense, like maybe models where you're used to thinking about the answer being robust, wouldn't fall into this framework. So that's one thing to say. And then about the sub-exponential time, we do get sub-exponential, like we do get results in the sub-exponential regime, but there, I think we're not exactly, like for example, for tensor PCA, we don't get exactly the correct answer. So the trade-off of runtime to, sample complexity isn't perfect for tensor PCA, but it does give something. I mean, some lower bounds for SQ.
Thanks a lot. Yeah.
Oh, well, of course, Prasad is normally here once he's overcome the COVID scare from his child. And so, yeah, for people who are here, of course, you should go talk to Prasad throughout the semester. And if you're on the internet, you can, I'll volunteer you, Prasad, to answer people's emails, questions. So thanks very much, Prasad, for wonderful 4 lectures. Yeah, so thank you.